Now when we want to prove A union B equals probability of A minus probability of B, A plus probability of B minus A union intersection B, we can see the picture here, but we have it in bigger in here. We can see how the both sets are in here. This is 1 and this is 2, A and B. A union B equals the union of 1 and 2. So the probability of A union B equals probability of I plus probability of 2, as we know it from the axioms. Probability of A plus probability of B intersection A. This is going to be our first part, and we will replace it later. So now we need to find this probability that is in this part. So probability of B intersection A complement equals probability of B minus probability of A intersection B. So B, probability of B, we can see that is B intersection A complement union A intersection B. Probability of B equals probability of B intersection A complement plus probability of A intersection B. And the probability of B intersection A complement equals probability of B minus probability of A intersection B. This part, we are going to replace it in here, and we are going to achieve the probability of A union B, proving that the probability of A plus the probability of B minus the probability of A intersection B. Having like this, the proof that we were looking for previously. Here we can find the three axioms, where we can see that the first axiom of all is that the probability of the sample space is always going to be equals to 1. The probability of E1 plus union E2 union E3, we can't split them and add them apparently, as we just shown in the proof, and that the probability of the event is going to be greater or equal to 0. Continuing, here we find what conditional events are. The probability of an event A given that another B has already occurred. So this conditional, for example, here we can see that in this case A depends that B has already happened. So B needs to happen to occur so that the event A can happen. This is what we meant by conditional events. The conditions of independence we can see in here, where we can look that events are independent if their joint probability equals the product of their probabilities. So for example, we see like the probability of A intersection B equals probability of A times probability of B. So this means that the probability of A equals probability of A times probability of B over probability of B. Probability of A intersection B over probability of B equals a probability of A such as that B has already occurred. This is what we meant by independent conditions. Now going further, we can analyze the sample space, for example, for 3 coins. One tip we have for finding the sample space of these 3 coins is first writing head, tail, head, tail, head, tail, and head, tail 3 times this combination. Afterwards, we write 2 heads, 2 tails, 2 heads, as we can see, and finally 3 heads, 3 tails. And here we're going to have the total sample space for the flipping of 3 coins. This is one example of the experiments we can make in probability. Okay. One of the other examples, we can see the probability of one dice of 6 sizes, a normal dice. We need to find the probabilities. So probability is going to be 1 again, that is going to be the same, so we can write it only once if we would like to. 2, 3, 4, 5, and 6. Passing to the probability distribution, we see that probability distribution is a function of a discrete variable whose integral over any interval is the probability that the random variable specified by it will lie within the interval. Now we can take a look of what mutually exclusive events are. So 2 events are mutually exclusive if they both cannot occur at the same time. Okay, this is the definition of mutually exclusive. If we go further, we can find what a normal distribution is. And normal distribution is a continuous distribution to represent real valued random variables whose distribution are not known. For example, a normal distribution would be doing an analysis of a demographic section of any country or any place that we would like to prefer, and finding this representation. The area under the curve of this graph that is achieved from the normal distribution is the standard deviation of the mean of the events that are occurring in this space. Now we can take a look of what Bayes' law is. Bayes' law describes the probability of an event based on prior knowledge or conditions that might be related to any event. This means that Bayes' law stands that the probability of A intersection B could be written as the probability of B such that A already occurred times the probability of A, and the same way the other way around. In this case, we have that the probability of A intersection B over the probability of B can be written as the probability of A such that B has already occurred. This is the 3 axioms, the 3 stages that Bayes' law states. Furthermore, we can find what the tree diagram for flipping three coins would look like. We can see how this would be the tree diagram for flipping 3 coins. So firstly we start with a head and a tail, and from each one of them we take out 1 head, 1 tail, and Again, we repeat the cycle until we reach all the possible answers. Having here head head, head head tail, head tail head, head tail tail, tail head head, tail head tail, tail tail head, tail tail tail. Being all these, all the possible outcomes that we will reach by flipping all the 3 coins. Now we can see what binomial distribution is. We can see that the experiment consists of n ideal trials. Each trial results in one of the 2 outcomes called success or failure. The probability of success, denoted by pi, remains the same from trial to trial. The n trials are independent. So we see how the standard derivation for a binomial distribution will be the square root of n times p times 1 minus p, and how the mean would be n times p. What binomial distribution shows is the success in a sample size n is useful when the size of the sample is big and calculations are very long, so we can find any probability in a faster way. Here, when we want to find the probability of A such that B has already occurred, or the other way around, where a probability of B where A has already occurred, we can see that this can be found by doing the cardinality of A intersection B over the cardinality of B, or the other way around, cardinality of A intersection B over the cardinality or probability of A. And in here we can see what a normal distribution with a normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal deviation. This one was one of the questions we need to explain. So when we have a distribution, a normal distribution, like we already explained it here, with a mean of 0 and a standard deviation of 1, this is called a normal distribution. And the menus we used for reaching this are the NCD and INVN.